Welcome to this presentation on the modelling and hydrostatic capabilities of applications in AVEVA's initial design suite. The applications in this suite cover surface design, layout modelling, and naval architecture analysis. These are standalone applications, but even so they're very powerful tools with very easy to understand and learn user interfaces. It means that you do not have to use them every day. Even as an occasional user, you can come back and remember to use all the powerful facilities that these applications offer. The applications are based on over 40 years of experience working in this area. It goes as far back as the British Ship Research Agency. This transitioned in software terms into BMT. These applications that were then bought by KCS, migrated into Tribon, and a few years back bought by AVEVA. The workflow is worthwhile understanding. The applications are standalone but transfer data between them to make that process very easy to work with. The surface and compartment application can be seen as rather a central tool used for building up the geometry and the definition, assembling that into a state that can be then transferred onto the hydrostatic analysis or into the main AVEVA Marine suite. The lines tool is used for generating hull surfaces to a level of high production fairness. These tools can be operated concurrently. A mechanism exists to transfer the data from one application to another in a review update capacity. Once you are up to a particular stage where the next person down the line could benefit from that data, you can release that data. Then in the subsequent tool, when the project is open, they'll be notified that an update is available. It's then up to them whether they choose to use that update. They may not want to if they're in the middle of a calculation process, but if they do want to update it, these tools allow you to adapt that information into your current model in a very easy to consume way. Surfaces can also be brought into surface and compartment through the SAT interface. IGS files and step files may be used by transferring that through AVEVA's Surface Manager application. Geometry can be brought into lines, for example using the curve facility in IGS or using DXF. The hydrostatics tools produce mainly reports. These can be exported in the form of HTML, XML or LaTeX formats, and then brought into Office tools like Word. Diagrams can also be exported as geometry using DXF or Windows metafiles. Both geometry tools can feed into the main AVEVA Marine Design databases. Hydrostatic results can also be posted into the AVEVA Marine databases and then custom reports generated using the reporting tool. Let's now have a look at the individual capabilities of the applications in the suite. The AVEVA Lines tool produces sculpted surfaces, and you're really able to achieve a high level of production fairness with this tool. It works through using interactive curve modelling, allowing you to build up a topology or a network of curves across which a surface will be generated. Design is achieved through refining these curves. The application also supports hull transformations. At different stages you may transfer that surface definition onto surface and compartment. This tool provides a different set of surface tools, being much more constructive, having access to tools such as surfaces of revolution and lofting. You also have solid modelling tools to do things like unions, intersections and subtractions. So it allows you to build up a much more complicated model. Now, the tool is also used for arrangement design, and often the arrangement has to adapt to design changes. And in this arena, the tools used are far more dynamic than the original solid modelling tools. So when you start to produce your subdivision, you're generating surfaces, but these are parametric definitions, which means that if you decide to change the hull form, for example, then the subdivision and compartments can adapt to these changes. At this stage, really what you're thinking about is preparing your geometric definition for analysis. The tool features some checking tools to check your arrangement, to check where if you have accidentally double counted certain areas of volume or you've got a gap. You can also use the surfaces to do a very initial estimate of your light weight. When you're ready, you can move your data then into the calc tool. This can do a lot of reports on your arrangement and starting with some simple hydrostatic calculations such as form calculations and cross curves. You can then move on to loading conditions, onto damage stability, both deterministic and probabilistic. You can go as far as doing continuous flooding simulations to look at what happens in this situation if you're grounded and you're needing to pump water out of the vessel. There are also a range of hydrodynamic analysis, powering manoeuvring, seakeeping and dynamic positioning are supported. So let's have a look at the demo of the geometry tools. We'll look at surface and compartment. We'll start with an envelope based on an existing surface. We'll have a look at adding some appendages. We'll make an appendage in the form of this rudder here. We'll then look at the actual definition, the arrangement itself, with a weather deck, and then we'll add some internal subdivision and onto some very simple compartments. We'll then move on to a more mature definition, look at some of the more complicated compartments and tank shapes that you can make. We'll start by importing a hull surface. And this has been made in the Line software. So when we bring it in, because it's been made within the another application within the initial design suite, it has connected with it all the initial general particulars, and we can see whether it's the same size as the ones we're expecting. So we're making a comparison, and once we've done that, then we can, as it's a half hull, reflect it and cover it over so it's in a contained solid, which will help us turn it into a envelope. So it's now in, it's a solid there, and what we'll do is, because we need to start to model inside it, then we'll turn this into an envelope directly. So we just right click, set as an envelope, and an envelope is like a dynamic solid model, so we can go in and edit it, move things around, and we'll have a look in that in a wee bit later. So what we're going to do is just quickly turn it to being slightly transparent, and that means that we can see the inside of it when we're working with it. This particular one is going to get added to it some appendages. We could add a skeg keel and some thruster tubes. We can use pretty much any shape you want. We do have some azimuthing thrusters here as well. We'll zoom in on them. So we can use some volumes that we can design to take up volumes for the hydrostatics. And these have been designed in the software itself, and you know, to preempt that, we'll have a look at creating some simple shapes like appendages. So what I'm going to do is create a rudder, and here we have two curves representing the section of a rudder. These are based on NACA profiles that can be generated within the software. I'm going to turn these into a rudder shape with a set of different operations to kind of highlight what you can do. So we'll start out by lofting a surface between the two. And here we see one side, it's a one-sided surface, like all surfaces are in solid model. We'll just then go on to reflect it to create the other side. And as we go through, we can stick each of these pieces together. So we'll do a quick join there, capture it together. We'll now round off the bottom with a surface of revolution. So we're just going to take 180 degrees from the curve that's at the end, create a rounding, and again we'll stick that to the surface. We'll close off the top. This can be done with the cover hole function, and now we have a complete model. We can also go on to add things onto it. So for example, we could add a rudder stock, use a union to connect that all together. We could create a recess, say for a flap, use the subtraction to cut that away. Got some nice blending options to add curves that might be needed. So for example, in this particular case, we're going to round the edge up here. I will hide the curves because I can also select the curves with this. So if we now apply this to these two edges, there we get a rounding there. We can see that we've made a fairly complicated model quite quickly using the tools within the software. Okay, so we'll now return to the whole form and add these appendages, like the one that we've just created, the rudder, to the whole form itself. So we can edit this one, and we can just basically drag and drop in. So we have a keel there, we can turn that to a positive element, and you can see that it's now been absorbed into that surface, and the keel becomes a sub-element of the hull. The same with the thrusters. We can turn them to be negative appendages, and they get merged into our hull form there. We can still edit these appendages afterwards. So if we turn on thruster 2, you see it now becomes visible, and as it's a primitive, I can edit its parameters. So if I wanted to, for example, move that up by a meter, I can do that there. And we can zoom in, we can see that we've moved the solid, but at the moment the hull hasn't updated. We can also see that the hull has now a red cross on it, and what that means is that it's ready to be updated. It'll wait till I'm ready. So if I say, okay, update now, then it will move the hull. So this kind of approach is quite useful. For example, if we choose to change the hull surface to make some modifications, fair it can be brought in, updated, the hull envelope, and then any other elements that depend on the hull envelope can be updated subsequently. We'll now take the hull form and we'll chop that down to its proper shape. So we're going to create a working deck area on the back of the ship. So we'll start by using the internal surface editor to make this deck shape. So let's make a weather deck, and we'll position this at 8.1 meters. So simply like that, we can press create and correctly create a deck with inside the vessel. Now this particular shape has some shear shape, and we can add some points in for that. So what we'll be saying is that frame 75 we'll have a step and another step at frame 81. So going up 2.8 meters and then finally 10.8 meters, creating this step affair in the deck. Pressing apply automatically updates that area there. Now I can then go to the envelope and add the deck to chop it down. So now that deck forms the top of the hull form. It's chopping it off, which is also quite helpful when you're designing, because you want to leave a little bit more surface on there so you can make adjustments later on. And it's a helpful tool for chopping things down. At that point we can see we've got some curves, so we'll delete them, and let's hide the deck for now. So now we have a kind of an external shell that's useful for now creating some internal compartmentation. And using the internal surface editor, we'll carry on with this process to create some more internal shapes. So we'll start with some bulkheads. And using the frame positions which have been set up, we'll just go through and create a set that we know where they go. So knowing these positions, these can be added quite quickly. Like so. So they're presently going all the way through. Say now that we had some other elements that needed to go in, say for example such as a double bottom. We can add this directly in. We can also specify constraints where these should begin and end. So if we wanted to go between that bulkhead to that bulkhead there, we can apply them, and the deck is fitting in that area. So now we'll have a look at creating some internal compartmentation. This follows a similar process, selection or list of constraints, and we can also add in the other categories that we have here. So if I wanted to add a water ballast tank, for example, I also have a set of connections here, a set of categories, and then we just go through and select the limits that we want the tank or space to fit into. So there we have a space there, it's limited by its areas. So it's quite straightforward. You just go through the ship. There's also some interactive ways of picking out some tanks. You can also slice the ship up in the visualization, so it looks like a GA process. Slice it in profile, in decks, and use the slicing cursor to pick out the compartment where it happens to be within on the view itself. So once we've got some compartments, we can do things like looking at some of the properties. So if we look at the properties of that space there, you can see here the message window down below. We have a compartment with an area, a volume, and its particular centroid. You can get more details like that. So populating the model is pretty much the same. We can add more internal surfaces, we can add more compartments, we can start to merge compartments to make more complicated shapes. So if we look at the more complicated model, we can see more about this. Here we see all the longitudinal bulkheads and transverse bulkheads. We can see things like some of the corrugations that can be added parametrically. And once you've populated this one, it will happen to look a lot like this. So here we have the complete model. We've got some empty spaces that might be free flooding, although they're quite high up on this vessel. We can also see some of the complicated areas in here. So if I select the cargo space, you can see some of the internals structure of that. So this compartment has to be made by merging some of the simple compartments that we've seen me make in the first project together. So if we hide that, we can also see that we've got some shape compartments. These are made by generating solids, as I did with the rudder, and turning that into a compartment, just specifying that this solid is now a compartment. Some of the spaces are obviously going to get quite complicated. So if we see here now, for example, the engine room has quite a good deal of complexity with various escapes and the uptakes for the funnels, and the software handles this fairly straightforward with just some simple merges. So having modelled the compartment, the vessel and all the compartments within it, we could now send this off into Calc. But there's a few areas where we can get information out in Surface and Compartment itself. We have a compartment report, which we can use to generate a simple listing of the volume, the permeability, and the centres. And this is quite nice as an initial check. We can also go on to create shaded drawings. So this is quite nice for giving you views of the compartments and what they look like. However, my preference would be for unshaded models, because here you can see through the compartments, and that's quite nice if we were using this kind of report to send to authorities, for example, so that they could see the physical geometry of the spaces that you may have modelled and pick out any features that are not apparent from, for example, on the GA plans, for example. So following the compartments, what we would do is start to select all the information that we want to send forward. So effectively I'm checking the compartments that I want to send through into Calc. In this particular case I've got quite a lot of sub-compartments that I don't want to send through. And then it's just a case of releasing this to the calculation geometry, which can then be picked up by Calc. And as we said earlier, one of the advantages of this approach is the fact that I release geometry to calc when I'm ready. I can release early geometry that they can start their calculation process, for example just the hull form, and then once, for example, the compartments are populated, I can release them through, I can make changes, and when I've completed those changes they can be again released through, and the person conducting the calculations can read in those changes when they choose. They know that there's an updated model, but they don't necessarily have to bring that straight away if they're in the middle of a calculation, for example. Turning now to the hydrostatics, there's a great variety of calculations available in this software, from simple form hydrostatics and stability through to damage stability, both deterministic and the current probabilistic rules. Detailed loading conditions are also available. There's also minor calculations for regulations, for example equipment number, miscellaneous calculations for things like inclining tests and launching. There's complex simulations to look at flooding and pumping of water out of vessels. There's also calculations for specific ship types, say for container vessels or grain vessels. The software is very easy to learn. In fact, this is pretty much all you need to know. The calculations are arranged in a tree. You can see that each calculation is depicted by a calculator icon, and beneath it there's a report. You can configure a calculation by right-clicking on it and selecting the Edit menu. This will bring up a form, giving you the ability to configure all the details of that calculation. Once you close the form, you can then go back to the right-click menu, calculate, and it will generate a report. In terms of deterministic stability, the criteria details are very important. The software features a set of present criteria, but also new criteria come along all the time, and the system gives you the ability to generate your own. Presently there's around 26 different types of regulation from different regulations around the world, looking at different characteristics of the GZ curve, and also of other items such as downflooding points and deck edge. The form allows you to configure how you apply that rule to the GZ curve, the scenario you're investigating. There's also another range of healing moments that may be applied to each of those criteria. There's documentation to help you learn how this criteria wizard works, how you apply the specific characteristics, how you get particular important regulations such as here the IMO weather criteria, and how other types of criteria are applied. In this case, how you do minimum distance to the waterplane, for example, what that really means and how it's applied. The restrictions of using the limits or constraints within the criteria wizard itself. So now let's have a look at the demo of the hydrostatics tool itself. So we'll start with an overview, and then we'll go on to the calculations themselves, looking at the tree on the left of the screen, looking at how you configure each of the calculations, and then looking at the reports that are generated by them. So we'll start simple with some form characteristics, move on to loading conditions and damage stability, and then look at some of the smaller calculations and some of the hydrodynamics capabilities. So here is the calculation software, Hydrostatics and Hydrodynamics, also known as Calc. So we see on the left hand side of the screen we have a tree structure, a range of different calculations. So if we open the tree up, you can see that we have a little calculator depiction showing each individual calculation itself. In the center of the screen we have a report area. So here we can find output on each of the calculations that we have. So for example, this tank calibration for the base oil tank of this project contains a set of curves and also some tabular data with some images showing the details of the calculation outputs. On the right hand side of the screen we have a view of the 3D model, and this will show a graphical depiction of the context of the calculation when we select it. And in the lower section we have a view of the plan of the ship, a 2D version of the layout, if you will, which can be used to select compartments for loading and things like that, or just give us an overview of the vessel. So let's have a look at a simple calculation. If we go to the form calculations, for example, and have a look at the tables, we see that we've got some hydrostatics there, a range of drafts increasing from the light draft to the heavy draft every 0.1 of a meter. So if we go to the calculation, we go to the edit option, we bring up a form, and we have a form here that we can do all the entries that we need for this particular calculation. So for example, if we wanted a different range of drafts, we could delete them and add a new set. So instead of 0.1, let's go for 0.2 increments. We press OK, right click and calculate. We see that the calculation has a red cross on it showing you that it's not been generated. And once it has been generated, the red cross disappears. So now we have a table every 0.2 of a meter. Let's go a little bit deeper. Let's change some of the outputs. So perhaps we wanted to add the block coefficient and prismatic coefficient, removing the TPC and MTC columns. We go in, we find the option that allows us to do that. Remove these two options. We'll just add the block coefficient and prismatic coefficient. Again, calculate. And then we have those options added on. If we were looking to assemble something like a stability book, then we would want more than just these two options. So you can also imagine that what we're doing here is assembling a report. Each of the calculations appear in a sequential manner, which when printed out will appear much like a document with the areas there. So if we need more information to duplicate a calculation but change the parameters, what we can do is just simply copy and paste the options here. So for example, if we wanted to edit this and have 0.5 meter by stern, you can go in and change the appropriate calculations and parameters and update. So now we have even keel results, 0.5 meter by stern and 1 meter by stern. So that was the simple end of the software. Let me take you through to the beginning, and the beginning should start with setup. So at the top of the general particulars is the ship data calculation, although it's not really a calculation, it's just a placeholder for your primary data. So within here the reports will show things like main particulars, details of the ship, the calculation options, selected stability and frame table. So if we edit that option here, we can see that the form allows us to enter this information. So we have the main particulars of the vessel. We can set up the main dimensions, and when starting a new project this will come in from the project overall. At the bottom here we have a set of characteristics for the probabilistic section of the calculation, so it's quite important to get this correctly set so the calculation works correctly. And we can also set up now for the operation of the software on this tab things like the balancing accuracy, the trim accuracy, the number of iterations the software takes, setting up plate thickness, and below that these are properties that might affect the hydrodynamics characteristics of the software. We're also setting the seawater density here, the overall property. We can also set some specific water densities when it comes to loading conditions later on. On the Drafts Mark tab we can set up, in addition to drafts at the FP and AP, draft marks at particular locations where they would be on the side of the ship. The tables themselves allow us to enter stepped draft marks, so what we could do with this is represent the drafts along the actual positions on the points of the vessel where they're painted on the side. We can set up the stability criteria. Here we have our intact and our damaged sets. We set up our GZ curve, the number of degrees, its increment. We can also set up water on deck calculations. We have the option to locate the axis of stability. This is in the horizontal plane for vessels where there may be multiple axes of stability, where we might want to swing that around. So we're thinking vessels such as semi-submersibles. Software isn't really designed for those kind of vessels, but does have the capability to analyze it manually. Set up waves, bending on a wave, hogging and sagging, and we also have our frame table information that would again come in from the project if that had been set up previously. So this sets up our ship data. Now thinking a little bit about the arrangement, we have our tank plan. So here we have our compartments that we would load in from surface and compartment. We can set up their category, whether they appear on the tank plan, their damage permeability, their structural permeability, so affecting the amount of fluid or cargo that can be loaded into their space. We can also set up whether these volumes are buoyant or internal. We can also set up compartments to be free flooding. We have compartment categories. We would describe this as what a space is, its role, and that may include tanks and spaces that have a particular purpose, like a machinery space. Content types describe what goes into a space. A space may have more than one content type if it's a cargo tank, for example. We can also set up the grain angle for permeability, the colour that appears on the tank plan, and the ability of the cargo to absorb water, such as in the case of grain, rice for example. We also set the tank plan up here, the 2D view that you see on your report drawings. It's very easy to extend this to add some more views, so we could start by adding some sections. Let's add some 3 sections in here. So we'll set these to be sections, and we'll give them some appropriate positions. Like so. So we'll press OK, recalculate. This will take a moment, as during this process it's also generating the maximum free surface moments for all the compartments within the vessel. So once we're done, we can see we've got our tank plan, we've got our extra views that we just added in. We have our list of compartments, and these are listed with their default content types in the standard way that we would expect to see these being laid out in a standard report for a stability book or calculations submitted to authorities. We also have our content types. Going a little bit deeper in terms of software configuration, we can set up some options here that affect how the data is used. So if we don't necessarily want to use a commercial setup with the aft perpendicular being the origin, say if we were looking at a naval ship, we could switch this to be the forward perpendicular with it running towards the aft. I'd also highlight that the software defaults to positive being the starboard side, and this box here can be used to reverse that to make port the positive side. You can also set up options for the report, for example things like headers and footers on the output documentation, add your logo, set up whether you want to use black and white printing. As mentioned earlier, criteria is set up using the criteria editor. This allows you to set up all the configurations here. So for example, if we were to look at the module code damaged, we can go into here and we can see all of the different rules that we have available to us. We could look at the wind healing moments as well. So we have the ability within this tool to set up quite some complicated rules, collect them together, and then use that within the Deterministic Stability analysis or the loading conditions. So having introduced that side, let's look at some of the main core parts of the software. The loading conditions, for example. So we have a selection of loading conditions here. The first two in this list are hogging and sagging conditions. We see that if I select one of those conditions, my 3D view turns into a view of the loaded equilibrium state of the ship. You can see that the seawater is now wave shaped. We can see the wave on the side of the ship. That's obviously a complicated example, but we'll go for the simple full load condition here. So on this one here we can see that we haven't necessarily made the ship upright. And you can see the water plane also in the tanks showing that the vessel is heeled. You can see the contents of the tanks. So we found that the loading condition report is very much the conventional style with the plan view of the vessel, the compartments, floating position, GZ curve. We can put in the stability criteria, our points of interest. In this case here we have the deck edge, which can be reduced to 1 point for presentation purposes. We would have also our openings, and then we move on to our longitudinal strength characteristics. Looking at the options itself, we have an interface here which allows us to set up the fixed weights, the solid weights, and the fluid weights or cargo weights, weights inside compartments. On the left hand side of this we have the try option that allows us to see where we're up to. It doesn't give us the full stability characteristics, but it allows us to see what our equilibrium position is. So what we see in each of these views is a group of weight that can be used in this loading condition. Each of the information in here is shared between all of the loading conditions. We can turn it on and off to whether we want to use it or not. That's perhaps more significant in the load groups down at the bottom, where, for example, here I can set up a set of groups of tanks, fuel oil, running from 10 to 50 to 100%, and I can turn them on and off when I need. It highlights that if I've reused the tank in the other options, it will not allow me to select them more than once, so I can't double count a tank. But what it means is that this is a really easy way of setting up particular strategies of loading and just reusing them in new loading conditions as you generate new scenarios. If we want to edit one of these, for example, we can bring it up and it becomes just a simple table. You can see here my crew is 2.88 tons with a particular centroid. I've distributed it over the area of the accommodation, and that gives me an overall load. For the tanks, if we go into the fuel oil, you can see here by default it's bringing up the fuel oil category. I can set the level of loads, so if I wanted to load our day tanks further, I could push that up to 100, and when that happens the weight goes to, or the green is indicating they're fully full. I can also do that by adding the weight or the volume. It's the same in each. Also, it's possible to give a sensor reading if you've set up the sounding mechanism in the tank calibration tool. We have an option in here to set the content, so if we wanted to put in another type of fluid, we could also put in the rules that I want to use for the free surface moment in this particular compartment. So presently this is using the standard fixed method as defined by the regulations, but we could also use shift moment, the maximum free surface moment for that tank over its range of loading, the free surface moment at its 50% volume, or if we go for the given option we can type that in. So that's pretty much it for loading a compartment. Right, so we have option to include various lightweights as well. Now we'll have a look at some of the options that we can do with this, and these are controlling some of the calculation effects and some of the presentation effects. So here we can say whether we're checking stability criteria, forcing the upright condition, so setting the central gravity to 0 will force it upright. There's some opportunity to do some very basic submerged calculations. It doesn't go as far as doing conventional submarine calculations. We can force it to use even keel hydrostatics. This would be the case as if you had some very limited calculation results. Say you had a stability book that only had upright hydrostatics and you wanted to verify the results with that. We can choose other information, so we can set our seawater density, how we present the openings and deck edge, which state we want to present. We've got our longitudinal strength calculations, which can go into quite some detail, and that's ultimately, as we said, controlling what we see on the report. There are some automated loading operations that will allow you to do some tank balancing to understand the best setup. Also the homogeneous loading, and this can be helpful if you're not really getting a good layout of compartments, or you just want to quickly iterate through an even keel situation or even heel situation. Finally, we can start to incorporate some damage into that as well, and this will ultimately extend the loading condition. So within this area we have a set of damages. The damages are shared from the Deterministic Stability node. Presently they're not turned on. We can go and have a look at these a little bit later graphically, but if I decide to edit one, I get the full window of what's turned on in here. Now we can see that this compartment has two damaged compartments. They are both damaged to the outside waterline, and the propulsion room is also damaged. So if we turn that on, let's turn on another selection as well, and then go and do the calculations. So immediately see that my report is extended. I can run the calculation. It will now do the intact and the two damaged cases subsequently. So we get our intact case, and then we would move to our damaged case. So we can see the damaged rooms indicated in red, and then when we go to our compartments, we only see information about the damaged case. We don't see the original compartments, we see the subsequent information of what was damaged. Same for the other case. We have more extensive damage. In this one we have the whole cargo hold being damaged. You can see the extent of the damage in the graphical view up on the right. On the intact page we will get some summaries of these damaged cases right down the bottom. So down here we can see the damaged cases associated with this intact loading condition, and we can see whether it's passing the currently selected damage criteria. So we've started to introduce damage. The damage calculations in the software is separated into two areas. We have the deterministic area, it's just called stability, and the probabilistic area. Deterministic area is very simple to understand how it works. We have a selection of damage cases, and these were all of the damage cases that I had available to me in the previous loading condition. I just turned them on, I used them. There's the opportunity to create damage cases automatically. This will automatically generate one zone damages based on our bulkhead positions. But often for deterministic scenarios you'll probably want to edit them yourself, and you can do that in the same way that I showed in the loading condition. You can just go in and turn the damages on and off. Damage cases can be more than just damaged. We can extend that to look at, for example, grounding or set up the water on deck calculations. We can also specify which probabilistic zones this damage is part of, but in this case that's not really applicable because these are deterministic cases. Okay, we'll also get the opportunity within this calculation now to see some of the damage diagrams, and this is very helpful for understanding what is damaged. So again, much like the loading condition, this is shading in red the compartments that are damaged in these particular cases. On the damage states, we get kind of a matrix of the damaged compartments that are being damaged for each particular case. That's kind of helpful as well. So here we've set up basically our damage cases, and then we would want to calculate them. Here again we have, like everywhere else, another calculation. Right click and edit, and this is where we can specify the calculations for a range of drafts or displacements and trims, generate the limiting kg or the limiting GM curves for the whole setup. We select the damages that we want to use, and away it goes. It will calculate for some time. So what this will give us, working backwards, is a set of critical curves which we can use for our stability book. We'll be careful about choosing the criticals because there is a lot of information beneath that. We'll have a look what's going to go on there. So in the criticals, didn't take too long to present, you can see that we're just getting a table for each individual damage case of its compliance. On the condition report, what we get here will be the full damage stability calculations for each damage case when it appears. So this is a much larger report, more tables, so it takes a little bit longer to produce. You could use the options to reduce the amount of information being displayed. Certainly, for example, on the deck edge curve, that could be reduced a little. Depends on what you want to see in your report. So we will start with the intact state, and then it will move on to the damage states and just churn out all the intermediate results required to generate that limiting kg curves. So straightforward for the deterministic stability. For the probabilistic stability, it's again very much a automated process with some level of customization. The challenge with the probabilistic stability calculations is that they're much more complicated, which means that the level of customization that the user has probably has to be somewhat limited because of the amount of manual input they would need to do if they were forced to do that themselves. So it's a three-stage process. We start with the setup. This defines our regulations. So in this particular case, we're working with SOLAS 2009 using a 3-zone standard. Here we can set up whether we're using passenger ships, the size of the lifeboat, their position, that will take over for setting up our healing moments. We can also apply the SPS code for special purpose vessels. The surfaces are the geometric elements that we set up in surface and compartment to define our zone boundaries. We can tick them on and off, and there'll be active zone limits. On the permeabilities page, we'll be able to set up the permeability values for each of our different load lines. We can start them out by taking the default values from our compartment table, but that might not necessarily be the exact values required by the regulations, but it's a good starting point. Okay, so once we've done that, we can set up our zone information. So we can see the positions that we've set up for our zones, our compartments selected, their permeability. On the zones tab, those limits are drawn in different colours, and the areas of the vessel are shown here, Unfortunately, the font is a little bit big, but if you export this out to HTML or print it out to a document, then it's much more legible. So once you've set up your zones, then just as we did before, we will set up our damage scenarios. In this case, when you create damage cases, it's going to follow the flow of the probabilistic method. So you'll get your 1, 2, 3, and so on zone damages. Again, you can report on all of these in exactly the same way that we could do in the deterministic area. And then moving on to the calculation itself, again, same process, edit. We see now that we've got set up for our 3 load lines because of the rules that we're using. If we chose to use one of the other regulations, then the setup might be slightly different. We select the damages that we want to calculate against, and in this respect there's nothing more than we can really do. It's a case of pressing OK and running the calculations. So in terms of output, let's work backwards. So first of all, I will highlight that this vessel isn't really a probabilistic size vessel. It's too small, and because of that it's not going to give me the right results. In fact, it doesn't give me a required index because of the size. Not a good example, but I will endeavour to show you the flow. So what we will get out of this is the attained index here, and that can be compared with the required index. For our intermediate load cases, we can again get our attained index and required index and compare whether the individual load lines are complying. So above this, our table shows how the attained index is being accumulated, and for each zone the selected damage case, its stability, its probability and its stability associated with it to give it its overall p-value, s-value. Let's see, the overall attained index for that particular case. So at this point we might want to see how it is selecting these damage cases. So we can go to the subzone damage report, and within here for each zone it will give us the information for each damage case and its corresponding S value for its loading condition. So in respect, say for, let's take this group here, if we were to take the subzone 1-04-0-0S, it will take the worst damage case out of all of these for their individual load line, and we should see that that is the one that's presented in the next table that I showed you earlier. So we have a way of validating that. And then on the damage results page, we get is that for each load line we get the stability details corresponding to the calculation of S for each damage case. So we can validate the S value calculation for the particular floating scenario that damage case finds itself in. At the end here we have the detailed damage results. That shows us the detailed stability calculation for each damage case. I will not click on that because it will be rather a long report and it will take some time to present onto the screen. So for the purposes of this presentation, that is pretty much most of what I wanted to show in detail. But I will highlight some further calculations that come in the software. We have the tank calibrations, which we highlighted earlier. This will give you tank tables for each compartment if you choose it. It will also allow you to set up the sensor arrangement if you wanted to put in real sounding data into your loading conditions. We have the grain stability, so this will allow you to set up the grain calculations to account for trimmed and untrimmed cargo arrangements within the real geometry of the shape of the hold. It will allow you to capture the internal structure of those holds and how that corresponds to restricting the movement of cargo in those spaces, and then that information can then be used to support those types of calculation in the loading conditions. We briefly looked at the form calculations node, particularly with respect to our simple hydrostatics, but the software will also generate cross curves, sectional area curves, deadweight scales, and also some useful trim tables which give you information like, if I move a load of 100 tons, what is the change of trim? That simple kind of decision support style information. Under the regulations node, we see that we've got things like our gross and net tonnage calculations, freeboard calculations, floodable length calculations, equipment number for our ground tackle, and we should also find that if we decided to introduce a new node, we should have the updated oil outflow calculation here, and this can be used to deal with the allowable amount of oil that may flood out of a fuel tank or a cargo tank in respect of the current MARPOL regulations. Under the miscellaneous node, we find we've got those launching calculations and the inclining experiments. Beyond this, we have the hydrodynamic calculations, and within this we have the powering node, and this will allow us to set up our calculations for a range of different resistance extrapolators. We can take in the existing loading conditions. The range of methods is a good selection, covering a range of different vessels from conventional ships, VLCCs, planing craft, catamarans, a good relation, and it goes through the conventional process for calculating powering. If we do a calculation of that, you can see the types of information output, our summaries, optimum propeller, and just the resistances. The ratio calculation node allows you to take information from tank tests and manipulate the resistance extrapolators so that they more closely match the results from the tank tests. In a similar way, we've got the maneuvering calculations. These allow you to set up the IMO standard maneuvering scenarios. The calculation is based on the Clark maneuvering derivatives and a standard integration model. Let's see if we can get this one started up. Let's just take as a condition the full load and then do a calculation on that. However, again, it seems that my vessel is not necessarily set up because I'm doing a calculation on a naval vessel. So we see that the software is guiding us through. And let's switch to a merchant vessel. Let's say calculate again. Again, my vessel happens to be outside. So we have things like crash stop. We will have our turning circle. We've got our zigzag maneuver, and our reverse spiral maneuver gives us a little bit of information about the stability of the vessel in terms of its dynamic performance with respect to the rudder system. We could go on to seakeeping. This is quite an extensive calculation, gives you a lot of outputs. It's based on Lewis transforms or flanks close fit, and there's a whole range of output here from simple RAOs, basic operability, to voyage statistics. The final one is the dynamic positioning calculation, and this allows you to set up I would say positioning devices on the vessel such as thrusters, rudders, and then account for the environmental conditions, the wind, wave, and this will give you, for example, the level of redundancy in your system, and also the ERN number that's required for the DRNV analysis. So that concludes this demonstration. It's very easy to work through this software, very easy to run the calculations. It's in that respect very easy to learn. If you're not using the software every day, it's also very easy to retain the knowledge that you need to use it. So in that respect, for the occasional user, it's a very powerful piece of software. Having all the calculations together provides a very integrated tool, the ability to put all the calculations together and generate a report very quickly. And in that respect, you can get commercial style reports, quality presentations very quickly, deliver them to your customers, and get through what you need to communicate that information in a very powerful way. Thank you very much for watching the presentation.